Well, hi, welcome back. This is the next in my series going into detail on the different kinds of simple machines. So hopefully by now you've seen kind of the general overview of what simple machines are, how they work, how we do important calculations related to simple machines. The biggest one being the efficiency. And so in this particular video, I'm going to describe the details of inclined planes, and we'll do a problem where we calculate the efficiency of one of those. So the inclined plane is a little unique in that it's almost always, in fact, every time I've ever seen one used, it's only used to decrease the amount of force required to move something. And in plain English, that just means things are going to feel lighter than if you didn't use the inclined plane. So the most common example that most people recognize is if you have to lift, let's say, a heavy appliance into the back of a truck. It would be almost impossible for you to just get under it and lift straight up and put it on the bed of the truck. But if you build a ramp, what we would call an inclined plane, then you can use a lot less strength or force and still get the thing up to where you want it. So that's how we'll kind of think of inclined planes. The inclined plane is also related to two other simple machines that we've been through. I'm going to show you a page from the earlier part of the notes. So here's what inclined plane typically look like, and there's my example of lifting something heavy under the back of a truck. But if you look at a wedge, for example, the business end of an axe or a hatchet, is just two inclined planes put next to each other. So as you drive the inclined plane, let's say downward here, then you get a separation horizontally because of the wedge being wider here than where it started out. Also, a screw or a bolt is an inclined plane, because if you start on where the threads begin here and just wrap your finger around it, what you see is you're climbing in a way along that screw in what we might consider an inclined plane. So with a screw, what we do is we turn it, kind of rotate it, and then as the material that we're screwing into kind of climbs along that screw or bolt, then the motion that we get is, I guess, kind of up and down. So all three of those are ultimately different forms of an inclined plane. So let's look at this example here. Suppose we need to lift a 3-kilogram box, and 3 kilograms actually isn't that heavy at all. We would have no problem doing this. But let's say you're a little kid and you can't lift that much. So all we're trying to do is get this thing up to a height of 0.45 meters. So instead of lifting straight up like that, we're going to move this along the inclined plane. We're going to use 12 newtons of force in order to do that. So the question here would be to calculate the efficiency of this particular machine. So when we measure efficiency, we always do that as a percent. And just reminding you of what this is, it's the work out divided by the work into the machine. So what do we get out of the machine? Well, we give it some potential energy by lifting it up higher. What do we put into the machine? Well, that's our effort, our strength, pulling this thing along the ramp. And then to change it to a percent, we just multiply by 100. So we need to calculate these two numbers here, the work in and the work out, in order to calculate the efficiency. Remember to always show your work, and I mean all of the math that you're doing, show it on paper so I can see clearly the 3 steps. So this is the first step, writing down symbolically what the equation looks like. Now we're going to have to get back to this in a moment. We'll finish up over here. But first I need to actually figure out what these numbers are. They're not given to me in the problem. But as I mentioned, the work out is just the increase in gravitational potential energy. Those are the same number. So we're going to calculate it just the same way we did GPE, which is multiplying the mass of the object times the strength of gravity here on the surface of the Earth times the height that we give this thing. So the mass is 3 kilograms. G on the surface of the Earth is 9.8 newtons per kilogram. And the height that we're going to give it, Now be careful, make sure you're using the height number, not the distance along the ramp. Height is clearly a vertical measurement. And so we're going to multiply those together. I'm doing this on my calculator. And I get about 13.23. And then because everything is in kilograms, newtons per kilogram, and meters, then we can safely say that we're measuring in joules. Okay, so that's going to go in up here, 13.23 joules. Now I need to figure out what work I'm putting into the machine. Now this is typically the person, and so when it's a person using his or her own effort, we call this the effort force times the effort distance. Oops. My pen is getting ahead of my brain here. So up in the problem, we describe using 12 newtons of force. That's the person. So 12 newtons. And what distance does that force need to act through? The force is pulling along the direction, or maybe you can imagine somebody maybe pushing like this. But that's all along the length of the ramp, 1.32 meters. So I'll do that on my calculator. And I get 15.84. That is also in joules. Newtons times meters is equivalent to joules. So I'm going to put that up in here in my efficiency equation where it goes. And then I need to multiply by 100. So finally, I'm going to take those two numbers that I calculated, and just as it shows here, I'm going to divide them on my calculator. That'll give me a decimal number, and then I'll multiply by 100. That's how I turn a decimal into a percent. And I get about 83.5. I'll have to round at some point. 83.5%. Didn't leave myself a lot of space there, but I squeezed it in. So the efficiency, 83.5%, does that seem reasonable? Well, yes, there's no such thing as a machine with an efficiency more than 100%. And even to have 100%, we would need a perfectly frictionless machine. And there's no such thing as a frictionless ramp. In fact, this is a big efficiency number for a typical ramp. But I kind of made these numbers up. If you do this kind of thing in the lab, you'll find efficiencies much less than that. And in my class, my plan is to have you do a lab where you're actually measuring these things and figuring out the efficiency of the one that we have. So that's a good example of what a inclined plane problem looks like. It's not a whole lot different than the other simple machine problems. So give you a chance to practice some of this on your own. Thanks for watching. Good luck.